Yair is now going to present Exploiting Windows, Exploit Mitigation for ROP Exploits. I knew exactly what I was doing there. All right. Go ahead, Omer.
Have a good time, dude.
Okay. Hello, everyone. Thank you for coming. Let me get sorted, and we can start. Okay, so first thing first. Doesn't work? Okay. So, I bet your parents taught you well and told you don't listen to strangers, so I will introduce myself. I'm Omer Yair. I manage the endpoint team at Javelin Networks. We are a small startup that decided to protect your endpoint on the enterprise to protect your Active Directory from the endpoint. And Symantec believed in us and acquired us a few, 9 months ago. Even though I'm still not sure how I'm supposed to pronounce the new title. I'm also a photographer, and you can follow me on Twitter. So I want to start with the geist of this talk. It's a quote by Gilles Deleuze, a French philosopher, and he said the concept is a brick. It can be used to build a courthouse of reason, or it can be thrown through the window. And throughout this talk, we will identify all those bricks that make up ROP exploits, Windows mitigations, Windows exploit mitigation, and we will see how we can use those to break Windows. So what's on the agenda? We'll start talking about ROP 101. I will dumb down the things as much as possible, make it simple so everyone can understand. Then we'll talk about Windows exploit mitigations, and we'll see how we can abuse them. Next, about ROP mitigations, and we'll see how we can bypass them. And lastly, there will be a demo where you will clap hands, and if you will all behave yourself, there will be a little surprise too. So let's start. We can't start talking about ROP exploit without mentioning smashing the stack for fun and profit. And is there anyone in the audience that ever heard the term for fun and profit? Please raise your hand. Yeah, it's quite common, and I hope you all know where the source of this term came from. And it's an article by Aleph One that he wrote on 96 about the mechanics of the stack overflow. And we can't talk about stack overflow without explaining how stack semantics work. So if you call a function in a 32-bit processor, you first need to push the parameters on the stack, and the stack on my slides will grow upwards. And then when the call opcode is issued, the return address is pushed in the stack, and the instruction pointer jumps to the function that you called. Now that function will allocate space for itself on the stack, do its stuff, and eventually it will deallocate the space, and the retro opcode will pop the return address from the stack. So how Stack Overflow works? Well, let's take a hypothetical example, completely hypothetical. Let's say you have a program that gets an input and looks for details about the user. So it first allocates its space for the stack. Then it uses getS to receive a buffer from the user. Now a normal user will just fill up the few bytes of the buffer, but a hacker will start overwriting the buffer until eventually the hacker overwrites the return address. So now, if you are a lead hacker, you won't just write random bytes, you will write your shellcode instead. And on the place that you write the return address, let's say hypothetical again, you know the address of the stack, you can just write the address of the stack where your shellcode starts. So now when the return code will be issued, the instruction pointer will jump to the shellcode on your stack, and now you can run a shell. Now, this is not a hypothetical at all. That was the exact source code and the exact buffer overflow, exact shellcode that was used on the Morris worm, and that was 1988, almost a decade before Aleph One published his article on Stack Overflow. So the security industry actually knew about Stack Overflow and the potential hazardous disasters that it can make, but still didn't do anything, and it was so bad that it prompted the formation of the Third Coordination Center. So again, you would think that after Aleph One published his article, the security industry will wake up and start protecting everyone, but no, in 2003, all you had to do to exploit a buffer overflow was to write this simple HTML page, and that's a CVE but by Matt Miller. And what happened behind the scene is that Internet Explorer just replaced every slash character with an underline slash underline, which caused it to miscalculate the amount of bytes that it needed to write. And then it caused you to write like the first buffer to the stack, and you had the ability to override the return address, and then you could write the shellcode. But now this is not an OS where you can guess the address of the stack. This is Windows. It's a modern OS. Well, Yeah, then Matt Miller used a different trick. He knew that the system DLLs were always loaded to the same address. So he looked at those DLLs and found an opcode which is jump ESP, which was always on the same address. So instead of writing the address of the stack, he wrote the address of that command. So now when the return opcode is issued, the instruction pointer jumps to the jump ESP, and after it executes jump ESP, now the instruction pointer points to the stack, and you can pop calc if you want. Now you might ask yourself, well, how is it even possible to run code from the stack? Shouldn't it be just read-write memory? Well, that was possible a long time ago, until DEP came in on Windows XP Service Pack 2. And DEP, or data execution prevention, actually enforces the read-write, or more precisely, the non-execute code in memory. Because Windows, throughout time, always marked that memory as only read-write, but the CPU ignored that. And Windows had to add another bit, which is called the annex bit, which forces the CPU to actually not execute code on that area. And DEP was actually the cornerstone for ROP. It actually made ROP what it is today. And the reason why is because now we need a bridge between actually exploiting a software and writing our shellcode to that memory and running it. So ROP fills the bridge between those two things. Now another thing you might ask yourself, what do you mean that all DLLs are loaded to the same address? Well, again, that was the reality back then, until ASLR or other space layout randomization came. And with ASLR, every time you boot your machine, Windows randomized the base address of each DLL. So now you can't guess the address, you need to find it. Now, it is effective mostly on remote exploits, because if you can run code on the same machine, let's say you're trying to exploit a privilege escalation bug, well, you can just run a benign program that loads those DLL, and you know the address of those DLLs. So I want to take a little step back to help people that want to write exploits today to see some steps that we overlooked when we saw the stack overflow, because stack overflow looks very simple. You just write bytes and you control the machine. So let's see what those are if you want to write exploits today. First, you need to have a vulnerable software. You need to have access to that software so you can run your code again and again and again until you perfect your exploit to make it running well. Next, we had a way to gather information. So on the Morris worm case, we knew the address of the stack. On the Matt Miller CVE, we knew the system function addresses. Today, you will need an arbitrary read vulnerability that will allow you to leak those addresses when you run your exploit. Next, you need a way to manipulate memory. So Stack Overflow, obviously, you write the stack, so you have a way to write into the memory. You have other ways to write into memory, like heap overflow or use after free, which sometimes allows you to do that. And if you want to write exploit today, this kind of vulnerability is called arbitrary write. So if you have arbitrary read and arbitrary write, you probably have a way to exploit the software. And the last step, which I think is the most important to understand, is that you don't actually write code to the target process you are trying to exploit. When you hijack the code execution, it's actually a byproduct of both writing memory into that process and the normal execution. So if you think about the ret opcode that simply jumps into the shellcode from the Morris worm is the normal flow of execution of the program. And we abuse that normal flow of execution to run our shellcode. So now we're ready to play. So let's talk about return-oriented programming, or ROP. And the term was coined by Chovav Shacham on his article, The Geometry of Innocent Flesh on the Bone, which I think is one of the most amazing titles someone can give. And the main idea behind it is to reuse existing code in memory by leveraging the stack semantics. So let's understand how it works. In normal flow of execution, when your program runs, the instruction pointer and the instructions control the flow of execution. So every time an instruction is issued, the instruction pointer automatically advances to the next instruction. So now you have the instructions running one after the other. On ROP, the register that controls the execution is the stack pointer or the stack. So you are looking for a set of instructions that end with a ret. So now the instructions are running, and when the ret opcode is issued, the next set of instructions will be fetched from the stack, because that's the return address that's over there. So now you're running another set of instructions that are followed by ret, which fetches the next set of instructions. So now the stack pointer is controlling the execution, or the stack. And luckily for us, the stack is read-write memory, which we can control if we have the proper vulnerability. Okay, so one of the most important terms on ROP is gadgets. And a gadget is a sequence of instructions that usually ends with a ret that allows you to perform logical operations. Let's say you can copy a value into memory, you can change the memory permission of a memory area into executable, or load values into specific registers, and many more. Let's see an example. If you want to write an assembly code that write value into memory, you will probably write this code. You will load the value into EAX, load the destination into ECX, and then use the move opcode to move the data from EAX into the destination of ECX. So we are working with the stack, so we can replace the first two moves with pops. Let's see how it will work in a ROP. So you have the stack on the middle, and the memory and the code on the right, and the registers on the left. So we will start with the first set of instructions, which is pop EAX. Now you pop that beef into EAX, and the ret opcode will take us to the next set of instructions, which is pop ECX ret. So now we pop the address we want to write to, the 61230, and now the ret opcode will take you to the next set of instructions, which is the move EAX into ECX. So now we are writing the dead beef into the address we wanted. Okay, so most of the talks on ROP only mention 32 bits, but we are on 2019. It's about time we will start talking about 64-bit ROPs. So the main difference between 32 and 64-bit ROPs is that when you pass the parameters for a function, you need to load the first 4 parameters on RCX, RDX, R8, or R9. Next, you need to allocate 32 bits on the stack. You don't need to fill it with anything. And lastly, all the other parameters are passed similarly to 32 bits. How does it look like? Well, if you want to call a 64-bit function that receives 5 parameters, again, it's a pseudocode. You first push the first parameter to the stack. Now you load the first parameter into RCX, the second into RDX, the third into R8, and the fourth into R9. Next, you need to allocate the 32 bytes. And the call instruction works similar to 32-bit and pushes the return address on the stack. So very similar to 32-bit. And the example which we will see today will be 64-bit. So what do we do with a ROP? Usually you would want to call either virtual protect or virtual alloc. Virtual protect allows you to change the protection of a memory address into executable. So if you have the shellcode already in memory, you just need to change it into executable and jump to that address. Or you can also allocate using virtual alloc an executable memory and copy your shellcode into that address and run it. Now, because those two functions are the main targets of ROP, the endpoint protection will actually monitor those functions, and we will see later how they do it. So a lot of the time when you write ROP, most of the time will be wasted looking for gadgets. And I want to suggest you just to look at anti-DLL, and there are a few reasons to do it. First, anti-DLL is loaded into every process on the system, so you don't need to hope that the DLL you exploited before will be on that process, because anti-DLL is always there. So if you find the gadgets on anti-DLL, you might be able to use those gadgets on every other exploit you will use. And another thing that contributes to that is because anti-DLL is so close to the kernel, then a lot of the code on anti-DLL is handwritten assembly. And if you ever wrote assembly, you know that you write it once and you don't touch it. It just works. So now, if you find a gadget that it's handwritten assembly, most of the chances that it works from the very early version of Windows, sometimes even Windows Vista. And the gadget I will show you works from at least Windows 7. And that's a lot of power if you can write your ROP once and use it on every other exploit you will ever need. So let's see some gadgets on anti-DLL. So the first is the function RTL copy LUID, and that function even doesn't look if you are copying LUID. It just copies 64 bytes from the destination you give from the source into the destination. And how it looks like in assembly, it simply loads the value from the source, which is in RDX, it's the second parameter, into RIX, and copy that value into RCX, which is the destination that you gave it. But because we are writing the stack, we don't need to write the return address to the beginning of that function. We can skip 3 bytes directly into the second opcode, and now we have the gadget that can move RX into the destination RCX. Now there is a similar gadget that exists throughout all versions of Windows, the move RCX into the address in RX. It's in the function RTL set extended feature mask, and you can use it everywhere, but now you need a way to load values into RAX and RCX. So how you do it? Well, modern compilers are aware of ROP and will not emit pop RAX threat or pop RCX threat in their code. But what they do emit is like add RSP 58 hex bytes, which is just deallocating the stack for 58 hex bytes. But apparently, the byte 58 is pop RAX. So if you skip 3 bytes into the middle of the opcode, you get pop RAX threat. And that opcode exists in a lot of time in anti-DLL. And very similarly, if you're looking for pop RCX, you have the multiply XMM0 with XMM3, which allows you to skip 2 bytes, and now you have pop RCX threat. So now we have a way to copy any value we want in memory. Next, I want to show you another gadget, which is on anti-DLL check stack. Again, handwritten assembly, and I will soon explain to you why, because it first loads the top of the stack into R10, then the next value into R11, then it simply deallocates that stack and returns. And it's simply like writing pop R10, pop R11 read. And how do I know that this is handwritten assembly? Because only if you read the Intel manual back then when Windows wrote their code, you know that this was a more efficient way to write it. So I didn't want to show you pop R10, but if you skip just 1 byte, you have pop EDX. So now you can load both RCX and EDX, so you have 2 parameters you can pass to functions. So that's thing we can start working with. Another very important gadget, well, obviously not pop R12, it's the pop RSP, and this gadget is called the stack pointer, the stack pivot, because sometimes when you have exploit, you can only write a limited amount of bytes into the stack when you hijack the stack. And this gadget allows you to write the whole ROP into the heap or a place where you can write a lot of code and simply pivot the stack into that address. So now you just need to write the return address into the stack pivot, and you can have a ROP as long as you want. Now, one of the most powerful gadgets on anti-DLL is actually a function. It's called anti-continue, which gets 2 parameters, and I can tell you that you can completely ignore the second parameter. It doesn't do anything. And context is contains the processor-specific register data, which means you can actually replace all the values in all the registers of the currently running thread. So now you can control not only R6, RDX, R8, R10, R9, you can also control the stack pointer and the instruction pointer. So that's a very powerful gadget that you can use. Now the last gadget I want to show is RTL move memory when you want to copy a large amount of data between memory. Now I like to make analogies because it better explains things, and I want to compare gadgets to the art technique called the ready-made. Okay, so the ready-made technique was invented by a French artist called Marcel Duchamp. And if you think the French people only contributed to the world by inventing, I don't know, like croissant, baguette, democracy, and mimikatz, then they did some other stuff as well. So this is this art piece called Fountain, which is just urinal turned on its side and signed with his pseudonym, Armut, which Marcel Duchamp did. And what he writes about it explains exactly, I think, what gadgets are all about. Whether Mr. Matt with his own hands made the fountain or not has no importance. He chose it. He took an ordinary article of life and placed it so that its useful significance disappeared under the new title and point of view, created a new thought for that object. And if you think about it, that's exactly what we are doing with gadgets. And if you follow this train of thought, well, like the fountain is an art piece, our little gadgets are little pieces of virtual arts. Sorry? So if you follow this train of thought and our gadgets are little pieces of art, it actually makes anti-DLL the public bathroom of Windows. Okay, so with that thought in mind, let's move on to Windows exploit mitigations. We'll start with stack canaries, and stack canaries protect you against buffer overflow. It works by first generating a random base canary value whenever a process is started, and then it writes a cookie into the stack using a calculation on that base value. Now, when the return opcode is issued before the return opcode is actually executed, it performs the reverse calculation and checks that the value we got is the base canary value. So now we can actually see if someone actually overridden the stack. And let's see a pseudocode, how it works. So it first loads the base canary value into ECX, then it stores the value with the stack pointer. So now it's not only as an attacker, you don't only need to guess the base canary value, you should also guess the current stack pointer, which is very hard, and then you push the value into the stack. Now, before the return opcode, let's say an attacker actually managed to override the stack, the opcode will pop the canary stack the canary value from the stack, will XOR it again, and will call a function that verifies if the value was changed, and because it did, it will actually crash the process. Next mitigation I want to talk about is the Windows 8 ROP mitigation, which is a very big name, but it actually just detects stack pivots. So whenever you are calling memory functions on Windows, starting from Windows 8, it will actually check that the stack pointer points to a valid location on the stack. So if you used a stack pivot on your ROP, well, Windows will detect it and will crash the software. And now, it's very easy to guess how you can bypass it. You simply need to make sure that the stack pointer points to a valid location on the stack when you are calling Windows 32 API. So how can you fetch the stack pointer value? Well, you can abuse stack canaries. So for the first technique I will show you, I call it a little bear told me, and we will see how we can abuse using a ROP stack canary to fetch the value of RSP. And the main steps we will take is we will first prepare the registers, then we will call a benign function that uses stack canary. We will fetch that cookie from the stack. You can treat it like a use or read after free vulnerability. And then we'll XOR that value with the base canary value. And if you remember before, I told you that you need to have a memory read vulnerability. And if you have that memory read vulnerability, you can actually fetch that base value from the DLL you are calling. So we will assume that we have that value on the ROP already. So you have the code on the left, on the top right, you have the registers, and on the bottom right, you have the stack. So the stack is also split between the address on the left and the values on the right. So we will start with a pop gadget, which will pop the values that we want. We want to prepare the registers. The important registers we're preparing now are R6 and R9. R6 is a parameter for the function we are calling, and R9 you will see later what it is used for. And now the ret will take us to the next function, which is RTL is valid process trust label SID. What it does, I don't even care. The only thing I care about is that it uses stack canaries and it doesn't mess up with the registers or the stack itself. So first this function allocates place on the stack. Next it fetches the base canary value into REX. You can see it over there. Now it will XOR the value with the stack pointer. So this is the stack cookie we're using. And later it saves that value into the stack. So you can see the same value on REX. You can find it now on the stack. Now, because we passed the parameter to the function, we passed a bad parameter, and the function will start to go into the exit sequence. So now, right before calling the ret opcode, it fetches the value, the stack cookie from the stack into RCX. Now it will XOR it with the stack pointer. So now we have the base canary value, and it called the functions that check the cookie. And because we are innocent, we didn't do anything wrong here. We're just calling a function. Well, that function will pass correctly. And now, before I execute this, I need to remind you the canary cookie is still on the stack. So we are deallocating the stack, but actually the stack memory is like a memory in any other place on the computer. So if no one written or overwritten that value is still there. So now we will jump to a special gadget that will allow us to fetch that value. And that gadget is in RTLP execute handler for exception. Again, all the gadgets you're seeing here are from NTDLL, and this is handwritten assembly. And you can guess it's used for exception handling, but this gadget actually allocates space on the stack, and now it calls, you can see that now we have the cookie on the stack, on our stack value. And now it will call a pointer that is controlled by R9. So if you remember the first gadget we used, we popped R9 to control the value. So can you guess where we are going with this now? What gadget we will use? Well, we're going to the same pop gadget that we used before. So now we are popping values from the stack. And the important thing is that now R9 will receive the canary cookie. So now we have the cookie on R9. All we need to do is to fetch the base canary value and XOR it. So now the ret opcode, you can see it will take us to the next gadget, the pop REX, you know that one. This will fetch the base canary value into REX, and the ret opcode will take us to the last gadget, which is XOR R9 with RAX. And this is part of RTL decode system pointer, another function on NTDLL. And now we have the stack pointer, and we can pivot from here and continue our ROP. Okay. So now for the next mitigation, we will talk about control flow guard, or CFG. And the idea behind it is to mitigate control flow hijacking of indirect calls. What are indirect calls? Let's say you're writing CPP code, and the compiler needs to fetch the address of the function from the virtual table. So it will emit code which looks like this. It fetches the address of the function into RAX, then loads the parameter RCX, RDX, and R8 for like 3 parameters for this function, and will call RAX. So CFG actually replaces RAX. Wait, I'll take a step back. If you are an attacker, you can actually hijack the value that will be saved into RAX, and then you can call any function you want or any place in memory you want. So control flow guard actually replaces the control RAX with a call to guard dispatch. I call it FPTR. Sometimes it's just a check and there is another call RAX later. It depends on implementation. But actually this function will check that RAX is valid function and no one overwritten it. How it does it? It uses a huge bit field where every bit marks if a function starts at a specific address in memory. So it's a coarse grain. It doesn't know if those are the functions you actually wanted to call, but if there is a function starting there and it doesn't matter what DLL it is, it will say that it's valid. What it gives us is that you won't be able to call in the middle of function and then mess with the stack itself. So now comes the questions. How can we abuse CFG? Well, we already did. Do you remember I told you that the CFG replaces the call with the call guard dispatch I call FPTR? Well, actually that function translates into NTDLL functions called LDRP validate user call target. And that function checks the bit field, you can see it, and down below you can see that if it finds that there is no function over there, it jumps into LDRP handle invalid user call target. And if this name sounds familiar, because that's the POP gadget we just used. So thank you, Microsoft, for introducing one of the best gadgets for ops out there and making it available in every goddamn process on the system. Now I need to ask sorry for all the people exploiting this, because if Microsoft is watching this, they probably take it away from us. But wait, there is more. If you will look at the MSDN, you will see there is a function called set process valid call targets. And this function actually allows you to tell CFG what addresses are valid. So let's say if you can potentially exploit indirect call twice, you can first call set process valid call target, set the target you want as a valid target, then call it again. So what do you think? Do you think Microsoft actually protect a valid function that is published on MSDN? Well, apparently they do. So nice one, Microsoft, but not that nice, because if you look at set process valid call targets, it's actually a wrapper around an NTDLL function called anti-set information virtual memory. And you know what? Anti-set set information virtual memory is actually valid called indirect target. So you can call this function, tell Windows that it's a valid target, and then abuse the same exploit again to run whatever function you want or whatever others you want. It's actually like telling Windows, those are not the exploits you're looking for, and you know, the force is powerful and the weak-minded. Okay, so let's talk about ROP mitigations. And we will talk first about ROP guard, which is the mitigation that is implemented by most endpoint security today, or at least a variation of it. And it uses strategic hooks on a memory function, like I told you before, on the virtual protect, virtual alloc, all the matching NTDLL functions, and all functions that allow you to create processes. And what it does, it fetches the return address from the stack and look at the opcode preceding it to see if there is a call to that function. And if there is a no call opcode before the return address, then how did this return address go to the stack? Now, it doesn't only check that there is a call, it also checks that the call opcode actually calls the function that we are hooking. So that's the ROP guard. In general, it does have some more tricks to do, but most of them simply checks that there is a call opcode. Now, K-bouncer is like ROP guard on steroids, if you would like. It actually utilizes a feature on CPU called last branch records, which saves the last indirect jumps or calls you had. So you have the source and the target address, and you can actually perform similar checks to ROP guard on those addresses too. So if you can think about it, ROP guard actually checks that the return address, which is the future of execution. K-bouncer also checks the past of the execution that already happened. Now I know that there are very few vendors that implemented K-bouncer, but most of them only implemented ROP guard. Now another mitigation is ROP packer, which I haven't seen implemented anywhere. And the idea behind it is to use the same mechanism as DEP, the data execution prevention, to mark all the memory as non-executable except for the current executing page and the next one. So now whenever the execution jumps outside of that area, there will be an exception thrown, and ROP packer will catch this exception and will perform similar checks to K-bouncer. But because it happens a lot, the heuristic that it uses are a lot weaker than K-bouncer. Now the last mitigation I want to mention is Shadow Stack, which is a collaboration between Microsoft and Intel. It was first proposed on 2016, but it was never implemented. They suggest to use two different stacks. One, the regular stack that you have and we all know about, and another matching kernel stack that only saves the return address. So whenever there is a call opcode, the return address is pushed both to the user mode stack and the kernel stack, and when there is a ret, it will pop both addresses. And if the addresses are incorrect, well, then you know that someone overwritten the stack. But as I said before, it was proposed in 2016. There is no implementation of it anywhere that I know of. And let's see how you can bypass it. So before I will tell you my method, I want to suggest you a paper to read or a Black Hat talk to watch, which is called The Beast is in Your Memory by Daniel Lehman and Ahmed Rigza-Zadegi. And they explain how you can bypass ROP packer K-bouncer by abusing their heuristic. And if you think about it, when they say they're abusing their heuristic, they actually have an intention of being caught. And I don't like being caught. So this is why I invented a new technique called rite of passage, which allows you to bypass the ROP mitigations without even being caught or without going through any of the endpoint security's hooks. So we collected a lot of bricks so far, and there is still one more brick we need to collect to understand how we can completely break Windows. And this one is the system call. So syscall is the way you transition from user mode to kernel mode, and whenever you call virtual protect or virtual alloc or any other Win32 function, it usually translates into a system call function inside NTDLL. Again, handwritten assembly. So all of those functions will look very similar to NT-allocate virtual memory. It first moves the first parameter from RCX and saves it into R10. Next, it loads the system call parameter into EAX, and on the case of NT-allocate virtual memory, I think it's Windows 10, the value will be 18 hex. Let's say for NT-protect virtual memory, that will be 50 hex. So every function has a different number. Next, it issues the syscall command, and the syscall is actually the opcode that transition into kernel mode, but it always goes to the same function in kernel. So how does this function know which function you want to run? Well, it looks at EAX. So now it knows that because EAX is loaded with 18 hex, you want to run NT-allocate virtual memory. Now when the function finishes on the kernel, it will return to user mode and the function will continue. So as I said before, all the endpoint protection usually hook those functions. So now you have a hook on the function, and if your ROP goes through that function, it will go through the endpoint hook. Some vendors even go as far as override the whole function, so you will not even know that it's there. Don't know why they should do it. But you know what? They don't hook all functions. Let's say anti-yield execution, which is actually a function that does nothing. It's like the insecure function of a program, if you want. It just tells Windows, well, I don't know if I have anything important to do right now. Maybe you decide if I need to continue execution or someone else do the execution. It's a function that has no interest to anyone, maybe for us. But another thing that you can see, how do I know that this is handwritten assembly or a macro that just copies the same values everywhere? It's because anti-yield execution doesn't get any parameter. So why do you need to pass RCX into R10 if RCX holds no valuable data? Well, that's handwritten assembly. But we can actually abuse anti-yield execution or any other function on int_DLL which is not hooked for our cause. And how do we do it? Well, we will start with a pop_RAX ret gadget that loads the system call into RAX. Next, we'll use another gadget that you've seen before that allows us to load R10. So now we can also prepare the first parameter. And next, we will not call anti-yield execution, we will jump 18 bytes directly into the system call. And now if you look at it, we actually have a way to issue any system call we want using a ROP. And because we don't pass through any of the endpoint protection hooks, no one even know that our ROP was there, and no one will ever catch us. So I wrote a little tool which I will publish on my Git later. It's called the ROP injector, which first allocates a read-write memory into the target process. It writes the shellcode into that process. Then it will create a new thread on that process and injects the ROP into that process using get process context and get thread context and set thread context. And lastly, the ROP will modify that area into read-write execute using either a regular call to virtual protect or a rite of passage call to anti-protect virtual memory. And lastly, it will run the shellcode. So let's see how it works. Okay, so I want to change things a bit. So I will not pop a calculator with my demo. I will actually inject a ROP into calc in my demo. So you need to pass the process ID to the ROP injector. So now we will pass the process ID of the calculator. And we're injecting a regular ROP. And you can see that our shellcode injected created a mutex called pawn, so obviously it worked. Now I will tell you a little secret. Endpoint protection don't protect all processes on your system. They usually protect only the vulnerable like Firefox. So now when we try to inject, you can see that the endpoint protection caught the ROP. So now we'll try to run Firefox again, and we will use the rite of passage ROP instead of the regular ROP. Okay. And the endpoint protection didn't even see it coming or see it that it even happened. Okay. So okay, so thank you. You all behaved very okay, you behaved very nicely, so I have a little surprise for you. I have a mini talk. Okay, so welcome to the mini talk, exploiting a Windows exploit for mitigating rite of passage exploit. So at the beginning, I thought maybe I will show you like the blue pill and how to write a hypervisor to protect against rite of passage. But last month, there was a research by Nick Peterson. He called it Infinity Hook, which exploits the Windows event tracing mechanism to hook system calls on the kernel. So what Nick found out is that there is a struct in the kernel that every event log saves, which has a function pointer that needs to save the timing of the event that occurred. And he found out that you can actually replace that function pointer with your function pointer to your function. And now you have a way to get notification every time a system call was issued. So now we can hijack system calls. So obviously Microsoft responded that this is not a security boundary, so I thought, why not make it a security boundary? Yeah. So now every time there is a system call, we can actually check what is the return address and check that the system call matches the same function that this function came from. And if it doesn't match, well, we actually caught a rite of passage bypass, and it actually catches a lot of more kind of exploitations, not only that. So you can find Nick's work on GitHub. And okay, so takeaways. First, have fun. I mean, even though Microsoft tries to make our life harder, we can still enjoy it and do fun stuff with it. And we need to remember that ROP remains a viable threat even 30 years after its first incarnation. And as a security industry, we need to respond faster to those threats. And I want to suggest we can utilize the Brain Zone Academy to do that. A lot of the research on ROP came from the academy, and also the research about how to bypass the ROP mitigations. And there are a lot of great minds there that we can use. So let's do that. And lastly, break it to make it better. Okay, thank you very much. So I think we have about 10 minutes for a Q&A. 5 minutes? Okay, I can't see anyone. Yes. Okay, so the question was how much of the mitigation are transferable to the Linux world. So first I will say I'm not a Linux guy, I'm a Windows guy. But I think ROPGuard is transferable, K-Bouncer is also transferable. ROP Packer, I don't know how Linux manages the memory of the processes, but I think it's also will be transferable. And I think also Shadow Stack can be transferable too. So maybe all of them, it might need a little tweaks from the Linux side. Okay, any more questions? Well, I can't see. Okay, so thank you very much.